Hello and welcome to This Explainer. I am incredibly excited today to demystify machine learning and show you exactly how it's becoming the ultimate must-have instrument in the modern chemist's toolkit. For decades, chemistry has leaned heavily on physical intuition, trial and error, and just painstaking laboratory work. But today, artificial intelligence, and specifically machine learning, is completely revolutionizing how we interact with chemical data. By the end of this session, you're going to understand exactly how computers can learn hidden patterns from data to predict properties, discover new compounds, and basically accelerate your research faster than traditional approaches ever could. So here is our roadmap for today. 1. The chemistry data challenge. 2. How machine learning actually works. 3. The chemist's algorithm toolkit. 4. Training and testing those models. And finally, 5. Real-world chemistry applications. Let's jump right in. Starting off with Section 1, the chemistry data challenge. To kick things off, just think about this staggering reality for a second. As modern chemists, we are practically drowning in data. We're talking millions of molecular structures, thousands of complex reaction conditions, endless spectroscopic measurements, and massive libraries of biological activity records. Trying to analyze all of this manually to find a single promising drug candidate or that perfect catalyst, it's practically impossible. Unless, you actually enjoy making your grad students cry over endless spreadsheets. We simply generate data way faster than the human brain can process it. And honestly, that is the fundamental problem we're trying to solve here. Which brings us nicely to Section 2, how machine learning works. Fundamentally, machine learning is all about mapping inputs to outputs. We have our inputs, which we call features. In our world, features are just the measurable properties of a molecule, things like its molecular weight, atom count, or log P. Then we have our target. This is the final value we're actually trying to predict, which, in this scenario, is solubility. The model's entire job is to analyze these examples and figure out the hidden mathematical rules connecting those input features to the target outcome. Once it learns those rules, boom, it can estimate the solubility of a brand new molecule it has literally never seen before. Now, much like a standard lab procedure, running a successful machine learning project follows very exact sequential steps. It's a highly structured workflow. You start by defining your problem, say predicting toxicity. Then you collect your experimental data, and this is crucial. You prepare and clean it. You have to treat your data as the reactant here. If it's contaminated, your whole experiment fails. Next, you train the algorithm to learn the patterns, strictly evaluate its performance to see if it actually works, and only then do you use it to make predictions on new molecules. That prediction is your final high-value yield. So the learning process itself generally falls into two camps. In supervised learning, which is by far the most common in chemistry right now, you give the computer a strict answer key. You feed it the features and the target, and it learns the mapping between them. Unsupervised learning, on the other hand, is super fascinating because the data contains zero answers. The computer explores a massive database of molecules entirely on its own, identifying hidden patterns and independently clustering similar molecules together without any human guidance whatsoever. When we do use supervised learning, we're usually tackling one of two major tasks. The first is classification. This is when we're sorting molecules into distinct, discrete categories. We're asking questions like, is this molecule toxic or non-toxic? Or is this compound an active drug or inactive? The second task is regression. We use regression when we need to pinpoint specific numerical values. So instead of a simple yes or no category, we're asking the model to calculate exactly what the boiling point will be in degrees Celsius, or exactly what the precise percentage of a reaction yield will be. Okay, let's open up the toolkit. Section 3, the chemist's algorithm toolkit. One of the simplest yet absolutely foundational tools in our kit is linear regression. It relies on that classic algebraic equation we all know and love, y equals mx plus b. We use this when a chemical property changes approximately in a straight line with another variable. It is incredibly fast and highly interpretable, which makes it perfect for estimating linear properties like density or baseline solubility. But let's be real, chemical relationships are rarely just simple straight lines. For more complex problems, we rapidly scale up to some incredibly powerful algorithms. We might use decision trees, which make predictions through a sequence of questions, like asking, is the molecular weight greater than 300? If yes, go down one path. If no, go down another. We can even group hundreds of these trees together to create a random forest, which significantly boosts our accuracy. Need to draw complex mathematical boundaries? We've got support vector machines for that. And at the absolute cutting edge, we use deep learning neural networks. These are systems inspired by the layers of the human brain, and we use them to tackle massive, incredibly complex data sets, like generating entirely new molecules from scratch, or predicting how complex proteins fold. Moving right along to Section 4, training and testing models. Now, the absolute most important rule in machine learning methodology is how we handle our chemical data. We never, ever let the model see all the answers at once. Instead, we typically split our collected data into 3 distinct batches. The vast majority, usually exactly 75%, goes into teaching the model. That's the training data. Then we use a 12.5% slice to validate and tune the model's parameters while it's learning. Finally, we hold back a totally unseen 12.5% test slice to strictly evaluate its final performance. So why go through all the trouble of splitting the data? Well, it's to prevent a massive pitfall known as overfitting. Think of it like calibrating an instrument. If your model just memorizes the exact noise in your calibration samples, that is overfitting, and it's going to fail completely on real unknown samples. What we actually want is generalization. We want the model to learn the true underlying chemical trend connecting structure to function. That ensures the model actually succeeds when we give it entirely new molecules it's never seen before. To evaluate how well our model actually generalized on that test data, we look at performance metrics. If we're doing a classification task, say predicting toxic versus non-toxic, we usually start by looking at accuracy. This one is pretty straightforward. We simply divide the number of correct predictions by the total predictions made. So if the model predicted 90 out of 100 unseen molecules correctly, bam, we have a 90% accuracy rate. But here's the thing, accuracy isn't everything. We also critically need to examine precision. Precision is all about the reliability of our positive claims. If our model tells us, hey, this molecule is an active, life-saving drug, we really need to trust that prediction. High precision ensures that when the model says yes, it is highly reliable, with very few false positives. In drug discovery, chasing a false positive wastes massive amounts of time and funding, making precision an absolutely vital metric. Now, when we switch over to regression tasks where we're predicting exact numbers like boiling points or reaction yields, we need different metrics. Here we use the mean absolute error, or MAE, to calculate the average magnitude of the model's mistakes. If we're predicting boiling points and our MAE is 2 degrees, it simply means our predictions are, on average, off by 2 degrees. Naturally, a smaller error means a superior, much more reliable model. And that brings us to the R-squared score, which is another absolutely essential metric for regression. R-squared measures how well the model explains the overall variability of the chemical data. Achieving a score of 1 means our model is perfect. It has entirely captured the variability of the chemical property. A score of 0, well, that means it has absolutely no predictive power and is basically just guessing the average every single time. Finally, let's head into Section 5, real-world chemistry applications. I want to make this crystal clear. Machine learning isn't just some future promise. It is happening right now in labs all over the world. It is radically accelerating drug discovery. It's drastically reducing the need for animal testing via rapid toxicity prediction. It's actively helping process chemists improve their reaction yield efficiency. It's being used to computationally design promising industrial catalysts, and it's even out there discovering entirely new battery materials for energy storage. It's a total game changer. However, as enthusiastic as we should be about all this, we absolutely must respect its limitations. These models aren't magic. If they are fed poor quality chemical data, they will output garbage predictions. It's the classic rule of computation: garbage in, garbage out. Plus, some of the most advanced models, like deep neural networks, can suffer from limited interpretability. They act as these black boxes, where we don't fully understand exactly why they made a specific prediction. Furthermore, for highly niche chemical properties, we often suffer from data scarcity. We just don't have enough experimental data to train the algorithms. And lastly, training these massive AI models requires significant, sometimes completely prohibitive computational hardware. So how do you actually become proficient with all of this? To truly master this modern instrument, your best practices should definitely include practicing a programming language like Python, getting hands-on experience exploring massive chemical databases, and really understanding the statistics behind the algorithms. But above all, and I literally cannot stress this enough, you must deeply understand your foundational chemistry principles. An AI model is just a tool. It takes a knowledgeable chemist to ask the right questions, clean the data correctly, and interpret the physical reality of the results. Well, we have covered a ton of ground today, from the immense data challenges and the algorithms to the vital importance of training metrics and the real-world impact. Machine learning is systematically replacing the slow grind of manual trial and error with rapid, intelligent prediction. So I want to leave you with this final thought to spark your curiosity. As artificial intelligence continues to reshape the very foundations of the scientific method, what incredible breakthroughs will you achieve? How will you use this superpower to push the boundaries of chemistry?